This is a revision summary of the AQA A-level chemistry topic of the reaction of ions in aqueous solutions. Although this is a separate topic to 3.2.5 transition metals, most of the metals described in this video are transition metals, so that's probably a better place to start if you haven't already revised that topic. Before we get into the meat of the AQA A-level chemistry specification, it's worth recapping some definitions that are important for this video. A coordinate bond, or it's sometimes called a dative covalent bond, is a covalent bond, so a bond in which there's a shared pair of electrons, but both of those electrons have come from the same species. A complex is an ion made from a transition metal, either an atom or an ion, which is then surrounded by some ligands. And ligands are species that can donate a lone electron pair. So that could be something like water or ammonia or a chloride ion. A Bronsted-Lowry base is a proton acceptor, and a Lewis base is an electron pair donator. The first specification point in this section is about different coloured complex ions that form when certain metal compounds dissolve in water. Now the nice thing is that these are all quite straightforward to remember because they're all these octahedral ions with 6 water ligands surrounding them. So all you really have to remember is the charges of each ion and also the colours they're going to be. Now copper is quite straightforward because you know that copper generally forms 2+ ions, particularly if you can remember the formula of copper sulfate, and you're used to working with that copper sulfate and you know that it's that nice vibrant blue colour. You've also encountered green hexaaqua ion 2+ ions, and they're going to be very, very similar. Then there's a colourless hexaaqua aluminium 3+ ion, and also the hexaaqua ion for ion 3+, and you've met that as a sort of orangey brown rusty coloured substance, but also under certain circumstances it can also form its monohydrate type, and then it's this sort of pale lilac-y violet colour. Now, the reason that the specification includes examples of complex ions that are 3+ and that are 2+ is because they want you to have this idea that the 3+ ions, so the aluminium and the iron 3, are going to have a greater acidity than the 2+ ions, so the copper and the iron 2. And the reason for that is because they have this greater charge, and so therefore they have a greater charge ratio because, you know, iron 3+ and iron 2+ are basically the same size as each other. And so they've got greater polarising power. Basically, they're going to attract the water molecules more strongly, and in doing so, they're going to weaken that OH bond in the water molecule so that it breaks more easily. And when that happens, we've then got free hydrogen ions, which are responsible for acidity. So now we can look at some actual reactions of aqueous ions in solution. And the specification is actually quite limited here. All it says is that you need to be able to describe and explain the simple test tube reactions of M2+ and M3+ ions with the bases hydroxide and ammonia and carbonate. So if we think about the hydroxides first, then you've actually met that exact same reaction at GCSE if you took triple science. And really nothing has changed. So if you add sodium hydroxide to a source of copper 2+ ions, then you're going to see a blue precipitate. If it's iron 2+, then we see a dark green precipitate. If it's iron 3+, then we see this orangey brown precipitate. And if we see aluminium, then it's this white precipitate. And as you know, if you keep on adding sodium hydroxide to that aluminium, it's eventually going to redissolve. Now, the slightly cool thing is that if you add limited ammonia, you actually get the exact same reaction, and not just something that looks the same, but you actually are making the same precipitate, say the copper hydroxide precipitate. And the reason for that is that when you add ammonia, that ammonia can act as a Bronsted-Lowry base, so it can accept a proton or a hydrogen ion. And those hydrogen ions have come from the water from the aqueous solution. So as each water molecule is being broken apart and dissociated, and the hydrogen ion is being associated with the ammonia, that leftover hydroxide ion is then free to interact with the transition metal or the aluminium. So what's happening is that even though you're adding ammonia, you're actually facilitating the production of more hydroxide ions, and so we still get this hydroxide precipitate. Now, of course, it wouldn't be fair if this was exactly as simple as GCSE, so we need to add another layer of complexity and we need to put some symbol equations into this. So we're going to start out with your hexaaqua copper 2+ ion or hexaaqua iron 2+ ion, and we've got obviously 6 water molecules in there, and one of these is going to be replaced by a hydroxide ion. So we then get this complex where we've got 5 water molecules and 1 hydroxide, and the water's been sort of ejected. And then another hydroxide ion comes along and does another bit of substitution, and we're left with this solid precipitate. So this could be summarised together, those 2 steps, in this single equation here. Or alternatively, if we've got our ammonia, then that is going to take 2 hydrogen ions away from 2 of these 6 water molecules here, and so what we're left with is that same precipitate alongside 2 ammonium ions. Now, aluminium is the interesting one of these ions because there's slightly more to it than just adding a bit of hydroxide and looking at a precipitate. So if you did triple science for GCSE, you already know that if we take those aluminium ions and we add some sodium hydroxide or another source of hydroxide ions, then we're going to get this white precipitate here. And you also know that you can then distinguish that from the white precipitates of calcium hydroxide and magnesium hydroxide, because if you keep on adding hydroxide ions, if you keep on adding an alkali, then eventually it actually makes this colourless solution here, and the white precipitate dissolves completely. So it will react with hydroxide, with an alkali, but also aluminium hydroxide will react with an acid. So we can say that it's amphoteric. So amphoteric is a word to describe a substance that shows both acidic and alkaline properties. So if you take A-level biology, then you'll have met the idea that amino acids are also amphoteric because they've got a carboxylic acid group at one end and an amine group at the other end. So anyway, this hydroxide is also going to react with acids. If we have a source of hydrogen ions, then we can turn it back into that hexaaqua aluminium ion that we had at the very beginning. We've already said that if you add a limited amount of ammonia, then that ammonia is able to function as a Bronsted-Lowry base. It can accept hydrogen ions and thereby generate a source of hydroxide ions, and can be responsible for the same partial substitution that you see if you add a limited amount of hydroxide ions. So if you take a hexaaqua copper 2+ ion and add limited ammonia, then we see that same pale blue precipitate that we would see if we were adding hydroxide ions. But if we continue to add ammonia, if we add excess ammonia, then a further substitution will take place. So if we start out with our hexaaqua copper 2+ ion, and then we've added a little bit of ammonia so we get some hydroxide ions generated, then we have this complex formed. It's not really a complex ion because it currently doesn't have a charge, because the 2 hydroxide ions are balancing out the 2+ on the copper ion. So we then add to that 4 ammonia, and the ammonia are going to replace the 2 hydroxide ions and also 2 of the water molecules. So what we're then left with is again a partial substitution. We've still got 2 water molecules in there, and they're going to be as far apart from each other as they can be. And then also the 4 ammonia molecules, and we've also got, being released because they've been replaced by the ammonia, 2 hydroxide ions and 2 water molecules, and this is accompanied by quite a vibrant colour change. It's obviously still blue, but we've gone from that paler blue that we have for copper sulfate to this really dark, deep blue solution. Hopefully that made sense, so pause the video and see if you can jot down an answer to this 4-mark question. Describe what you would see when dilute aqueous ammonia is added dropwise in excess to a copper 2+ ion solution. Write equations for the reactions that occur. So obviously the first step is that we have a blue precipitate formed, and this is going to happen with the ammonia turning into ammonium ions and 2 hydroxide ions taking the place of 2 of the water molecules. And this will then dissolve to give a dark blue solution. So we've then got that partial substitution that we saw on the previous page, and the 2 hydroxide ions and the 2 water molecules. Next on our list of test tube reactions is the reactions of these 2+ ions with soluble carbonates. So this could be either sodium carbonate or sodium hydrogen carbonate, which is sometimes also called sodium bicarbonate. And in each instance, rather than forming a complex ion with 6 water ligands, the metal ion is just joining up with the anion with the carbonate, and we've got the 6 water molecules being kicked out and left over. So in each instance we see a sort of a precipitate being formed. This one got a little bit bubbly, which it shouldn't really. Try and ignore that. That's just that my iron was a little bit dodgy when I took this photo. A green solution is thought to contain hexaaqua ion 2+ ions. Separate samples of the solution are reacted with aqueous ammonia and then with aqueous sodium carbonate. Write equations for each of these reactions and describe what you would observe. So with the ammonia, we're going to see a green precipitate, and the reason for that, as we said, is because that ammonia can accept hydrogen ions, it can release hydroxide ions, and so we've got iron hydroxide being made. So we're going to have this hexaaqua ion 2+ ion with a bit of ammonia, and then we end up with 2 of the water molecules turning into hydroxide ions, and the ammonia turns into ammonium ions. And then if we react it with aqueous sodium carbonate, then again we have a green precipitate being formed, and in this instance it's a complete substitution that instead of being reacted with the water molecules, the ion 2+ is now associated with that anion, with that carbonate ion, and the water molecules are evicted. The reactions of the 3+ ions are slightly more complicated than the reactions of the 2+ ions, but it helps if you remember that right at the start we said that the 3+ hexaaqua ions act more like acids than the 2+ do because they have that greater polarising power because of the higher charge. So if you think about GCSE and you think about how an acid would react with a carbonate, then you learn that acid plus carbonate makes a salt and carbon dioxide and water. And that's exactly what's happening here. We're basically having these hexaaqua 3+ ions functioning as acids and releasing hydrogen ions which can react with the carbonate, and then it just carries on exactly like it did at GCSE. So if we've got some aluminium hexaaqua ions to start with their 6 water molecules, then 3 of those water ligands are going to dissociate to make a hydroxide ion and also a hydrogen ion that can then go on, and those hydrogen ions can join up with some of the oxygen from the carbonate ions to produce some carbon dioxide and also some water. So what we see is a little bit of effervescence here and also the precipitate. So for aluminium this is going to be white, and for iron this is going to be this sort of orangey rusty brown here. Here's another exam type question. Describe 2 observations that you would make when excess sodium carbonate is added to a solution that contains hexaaqua aluminium 3+ ions, and give an equation for the reaction. Just quickly pause the video and jot down what you think the answer is. So our 2 observations are that we're going to see a white precipitate and bubbles, and if we wanted to we could take those bubbles and use them and try and turn lime water cloudy. In reality the amount of bubbling is actually pretty slim, so I'd be really surprised if you could manage to do this in your A-level lab, but theoretically it would work. And then the equation for this reaction is going to be what we've just seen. So if we've got those aluminium ions reacting with those carbonate ions, then we produce this solid precipitate and the carbon dioxide and the water. So now we're going to take that same solution, and instead of adding carbonate ions we're going to add aqueous potassium hydroxide dropwise in excess. So we need 2 observations that you would make and an equation for each reaction. Pause the video, write something down. So we're going to see a white precipitate being formed, and that's going to be where we've got 3 hydroxide ions substituting in for 3 of the water molecules. And then if we continue to add hydroxide ions in excess, that colourless solution is going to form instead. The white precipitate is going to dissolve, and this is because we're now making our AlOH4, which as we know is colourless. I hope you found that useful. If you did, then don't forget to like and subscribe and check out some of the other videos on the channel as well.